This is a demo of spectrum management using a modeling API. The sites you're about to see in front of us here are fictional, but the API is real. This is our API which we use for radio simulation. We're going to use two APIs, one for simulation and a second for interference analysis. The challenge here is making efficient use of spectrum, which is a finite resource. There isn't enough of it. In this example, we've only got 3 voice channels and a couple of radios here in the country which we want to deconflict. At the moment they are all green, there's no interference, they're all deconflicted, but let's take it up a gear. Let's go for 20 radios in this area. There's 20 random radios dropped upon the map here just to exercise the process. The first stage of the process is modeling each site, so we need to go and fetch layers for those sites so we can then proceed to the next stage and see how they interact with each other. All of those were modeled on channel 1, which is a bad idea because, as you can see, they're all stepping on each other. If we switch to interference, you can see a lot of strong interference here between these sites. So what we need to do is deconflict them using everybody's favorite magic wand here. So click the magic wand and it's going to compare those layers which we generated earlier and run lots of iterations through the interference API to find out how they play with each other and score them, and from there pick the least interference for a given pair of sites. So this is the result. You can see the 3 channels have been applied in what looks like a fairly random fashion, but it's not. It's based on scoring. I can see a splash of purple over here, and if I switch to interference I can see that there is indeed a bit of interference here. So I spotted that visually, but we also have the actual scores to compare numerically down here. So if you wanted to have a robot make this decision, then you can fully automate this using these scores. So that's nice, we did 20, let's take it up a gear and do 30. So we'll add in 10 more sites. Make it harder, it should take longer. It's knocking through these requests quite fast, as you can see, using a local soothsayer server. It's the same API as on CloudRF, and it's getting through these nice and fast. These are UHF portable radios that we're using just to bring this capability to life. And now let's hit the magic wand again. Whilst it's running, just explain a lot of spectrum data is sitting in databases, and the process for allocation requires a lot of manual analysis. So there's a lot of scope for automation to automate this process, and you can get away with doing it manually when there's only a few sites, but it does not scale to a large number of sites. It takes a very long time to do a study for a wide area, especially if you're talking about a satellite spot beam, for example. So we're deconflicted now. There's only a few sprinkles of interference, and you can see the scores down there. And if we wanted to now increase the number of channels, then we can go up to 4 channels and repeat the process of deconfliction to see what we could do with an extra channel. We should be able to eliminate interference by putting one of the interfering sites onto a new channel. Okay, so interference has largely been eliminated there, and we've done it in an efficient manner. Instead of allocating channels in an ad hoc fashion, we're allocating the minimum number of channels that we need in order to solve this problem and achieve spectrum harmony.